Assalamu alaikum students. I hope you all are good. Welcome to another lecture of chemistry. Today we are going to learn about an important topic, dipole moment. What is dipole moment? The definition of dipole moment says it is the product of the magnitude of charge and distance between the centers of positive and negative charges. Now, where do we observe these dipole moment in chemistry? We are going to find the dipole moment in some molecules, where we observe that there is development of partial or complete charges in a molecule. We have learned that in ionic molecule, there is complete charges on the atoms which are forming the molecule, positive and negative charges on a atom which are forming the molecule. Whereas in covalent molecule we find that when the covalent molecule is formed between the atoms which differ in electronegativity, that will lead to the development of the positive and negative, partial positive and negative charges on some atoms, creating what? A dipole or a pole species in a molecule. So whenever a polarity is present in a molecule, that molecule will act as a dipole. Those negative and positive poles, whether these poles are completely positive or negative or partial positive or negative, if there is charges in the species of the molecule, that molecule will possess some dipole moment. Okay. Now, what is dipole? How it is measured? You can say that dipole moment is the measurement of polarity in a molecule. What is dipole moment? Measurement of polarity in the molecule. So, if the value of dipole moment is high, it means the molecule is highly polar. If it is less, it is less polar. If it is zero, it means the molecule is non-polar. Okay, so we can use the dipole moment as a tool to identify measure the polarity in a molecule. How do we find the dipole moment? It is represented by a Greek symbol mu, which is equals to Q into R, where Q is the magnitude of charge and R is the distance of separation of the charges. Whatever is the length of the bond between positive and negative dipoles in a molecule, that particular charge separation distance is your R. It is expressed in the unit of dBi in the honor of the scientist dBi. Okay. Now what is dBi? The SI unit of dBi says that 1 dBi equals to 3.335 into 10 raised to minus 30 coulomb meter, where capital C is coulomb and small m is meter. So 1 dBi in SI unit equals to 3.335 into 10 raised to minus 30 capital Cm, that is coulomb meter. Now dipole moment is a vector quantity. It means it has a particular direction. It is represented by a small arrow on a molecule. So when you draw a Lewis structure of a molecule and you show a bond between two atoms, okay, you are going to draw a crossed arrow above that molecule, and the arrow would be headed towards the more electronegative atom with its tail on the less electronegative, or you can say electropositive atom. So here in example of HF is given, hydrogen fluoride. We know that HF has a covalent bond which is polar in nature. It is a diatomic molecule. That is a molecule made up of only two atoms. Okay. In hydrogen fluoride, hydrogen is electropositive and fluorine is electronegative. Okay. Or you can say that the electronegativity difference between H and F is very high, due to which what happens, fluorine being more electronegative pulls the electron density towards itself. So fluorine will have more coverage of that shared pair of electron. because of which a partial negative charge will develop on fluorine, making it a negative center or negative pole. Hydrogen is losing a shared pair of electron to some extent towards the fluorine. Therefore, hydrogen will develop a partial positive charge on its, okay, and you will say a positive center is developed. So to show the shift in electron density and the dipole moment, a crossed arrow is made on HF bond and the head of the arrow is towards the negative center and its tail is towards the positive center. Understood? Now it was what? A diatomic molecule having a bond between only just two atoms. Okay, so when we calculate the dipole moment of such molecule, it is very simple. It depends on the magnitude of charges on both these atoms and the distance between the HF, that is, you can say the bond length. Okay, so here the dipole moment is equivalent to covalent or bond moment. You can also say it is bond dipole moment. It depends only on that particular bond. The dipole moment depends only on that particular bond because there are only two atoms. Okay, now what happens when we have a polyatomic molecule? When we have a polyatomic molecule, now your dipole moment will not only depend on that particular bond, but some other important points or important factors will also affect the dipole moment. So dipole moment is going to depend on that bond dipole moment, as well as it will also depend on how the molecular orbitals are arranged, that is, what is the shape of that molecule. If any lone pair of electron is there, the arrangement of that lone pair of electron will also contribute to the resultant or total dipole moment. Okay, so in case of polyatomic molecule, apart from considering the bond dipole moment, we will also consider what is the geometry of that molecule, plus we will also see what is, if any lone pair of electron is there or not. If lone pair of electron is there, then that will also contribute to the dipole moment. Now the dipole moment will depend on three things: shape, bond dipole moment, and presence of lone pair of electron. Okay, now let's see one example. Let's take the example of beryllium difluoride, BeF2. Okay, now BeF2, let's look at the shape of BeF2. It is a linear molecule, okay, having a 180-degree angle between FBEF. Okay, so it is a linear molecule. Here beryllium is having a single bond with two fluorine atoms. Okay, now the two fluorine atoms are directed in opposite direction. You can see here one fluorine is on one side, the other is on the other side. Okay, now according to the definition, we have seen that dipole moment is a vector quantity and it is directed towards a fixed position in space. Okay, so we know that the dipole moment is directed from positive to negative center. Therefore you can see the arrow on both these bonds, where on one side the arrow is going from beryllium to fluoride on right hand side, and on the other side you can see the arrow is going from beryllium to fluoride on the left hand side. Okay, so we'll have two equal dipole due to that bond. Okay, but these two are going in opposite direction, so we have the dipole moment in equal and opposite direction, so they will cancel each other and there will be no net dipole moment of BeF2 due to the geometry of that molecule. Beryllium does not have any lone pair of electron, so it will not contribute to the dipole moment. Okay, so here two types of dipole moment were observed. One was due to the bond, but due to that bond we can see that as the geometry is linear, the two dipole moments will cancel each other and therefore there will be no net dipole moment for BeF2. So though in BeF2 there is development of polarity on the covalent bond, beryllium will have the partial positive charge, fluorine will have the partial negative charge, but still the dipole moment is 0, and there will be no dipole moment, means the molecule is non-polar. Okay, so if still we can observe the polarity in a molecule due to our knowledge of electronegativity difference, but on measuring the dipole moment you will come to know that there is no net dipole moment, therefore the molecule is non-polar. Okay, let's take one more example. Here an example of BF3 is given, boron trifluoride. In boron trifluoride, 3 bonds are made between boron and fluorine, and each of these bonds are placed at 120-degree angle. It is an angular molecule, okay, and it is symmetrical. Okay, again here what will happen, the you can find out the total dipole moment by adding the dipole of each of the bond. Okay, if you add the dipole of any 2 bond, it will cancel the dipole of the remaining third one because they are in opposite direction. Okay, so there again there will be no net dipole observed for BF3 due to its symmetrical structure. Due to the symmetrical geometry of BF3, the dipole moment of each bond will cancel each other and there will be no net dipole, and you will find that BF3 is a non-polar molecule. And again this happened due to the angular geometry of the BF3 molecule. Now let's see how the lone pair can affect the dipole or value of dipole moment. Now in some molecules, the central atom has unshared or lone pair of electron. These lone pairs also contribute to overall dipole of the molecule. Lone pair will also contribute to the dipole, I have told you earlier. Now let's see the example of nitrogen in ammonia and oxygen in water that possesses the lone pair and reinforces or increases the resultant dipole. Let's see the diagram, you will understand it better. Now here the diagram of NH3 and H2O is given. Now look here the resultant dipole is shown by the single arrow on right hand side of the diagram of H2O and NH3. Now you can see the dipole moment for ammonia is 1.48 and for water it is 1.85. Now here the dipole moment for each bond between NH is directed from H to nitrogen. In NH, nitrogen is more electronegative and hydrogen is less electronegative. So there is development of partial negative charge on nitrogen and partial positive charge on the hydrogen. So if you will draw the dipole moment for each these bond, all the 3 dipole moment will be directed in the same direction. Then again we also have what? A lone pair of electron, and the direction of lone pair of electron is in the same direction. So all these 4 dipoles will contribute and will give us 1.48 dBi value. Whereas in case of H2, again you can see that the oxygen is electronegative with partial negative charge and hydrogen is electropositive with partial positive charge. Okay, now again here what happens, the dipole of each OH bond is directed in the same direction and the 2 lone pair of electron will also contribute to the same resultant dipole moment. Understood? So why water shows higher dipole moment than the ammonia? Because water have one more lone pair of electron as compared to ammonia, which increases the resultant dipole moment for water. Understood? Here I have taken one more example of carbon dioxide and water. Look, in carbon dioxide and water, one similarity is there. Both are triatomic. Both are made up of 3 atoms. Okay. Now here in case of water, you can see water is angular, or sorry, water is bent or angular. Now this bent shape of water does what? You can see here the arrows are shown for dipole of OH-OH bond. Both the dipole are in the same direction, resulting in the resultant dipole moment. Whereas in case of carbon dioxide, the this thing dipole moment of carbon oxygen bond is directed from carbon to oxygen in equal and opposite direction, cancelling the net dipole moment of each bond, resulting in no net dipole. Okay, so carbon dioxide will have zero dipole moment, whereas water has a good dipole moment, and water is considered to be a polar molecule. Now, another example of ammonia and NF3 molecule are given. Now, you just look at the this thing, dipole moment of NH3 and NF3. For NH3, it is 4.90 into 10 raised to minus 30 coulomb meter, whereas for NF3, it is 0.80 into 10 raised to minus 30 coulomb meter. Okay, there is a huge difference in the dipole moment values of the two molecules. Now let's see what is the reason why NH3 is highly polar and why NF3 is not. Okay, let's look at the molecule of NH3 first. In NH3, you can see each NH bond is having dipole moment in the same direction. All these three dipole moments will add up, plus a lone pair of electron is also there, and the dipole moment of this lone pair is also directed in the same space, you can say same direction. So it will also add up to the three dipole moments of NH bond. So when all the dipole moments of the lone pair as well as of the covalent bond are in the same direction, as it is a vector quantity, all will add up and the resultant dipole moment would be some higher value. Whereas in case of NF3, you can see that the dipole moment is directed from nitrogen to fluorine for each NF bond. Okay, now each NF bond is having dipole moment for this covalent bond in one direction, whereas for lone pair of electron, the dipole moment is in the opposite direction. So because of this, it will get minus from the dipole moments of NF bond, and the value of NF3 dipole moment is less than the NH3. So the lone pair of electron have a very effective, or you can say influential effect on the total dipole moment of any molecule. The reason for this is given is here. Same thing is written here. In case of ammonia, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bonds, whereas in NF3, the orbital dipole is in the direction opposite to the resultant dipole moment of the three NF bonds. Okay, therefore the orbital dipole, because of that lone pair, decreases the effect of the resultant NF bond moments, which results in low dipole moment of NF3. The same thing I have said, because of the difference in that lone direction of their dipole of the lone pair of electron and that NF bond, there will be reduction in the net or resultant dipole moment of NF3. I hope you have understood the this thing, dipole moment. Dipole moment is observed when a molecule possesses a charges on some species of the molecule. If these atoms are separated by some length, and the magnitude of that charge will determine the strength of that dipole moment. Dipole moment also depends on the geometry of the molecule as well as presence of the lone pair of electron. So just go through this again and you will understand it better. Allah Hafiz.